we've seen how Newton's method can perform extremely well at optimizing a function in a relatively small number of function evaluations, which is one measure of how efficient an optimization method is. So Newton's method can and very often does work extremely well, but it does require that we can evaluate the Hessian matrix, and that's actually where a lot of the efficiency comes from, right? It comes from the fact that it's using a second order approximation to the function rather than a simple first order approximation to the function. So if we want to kind of get that benefit of that second order information, then we need to evaluate the Hessian matrix, but that comes at a cost. And for certain kinds of problems, it can be tedious to obtain, but for other problems, it can be really just very problematic to obtain, certainly in reasonable time. And so what we'd really like is a method that relies only on gradient information, like steepest descent, but performs better than gradient descent. Actually, has some of the faster convergence properties that Newton methods do. So that obviously is a little bit of a tall order, perhaps, to do in complete generality, but it turns out that there are a class of methods that do more or less do that. So they have almost the efficiency of a Newton type method, but only rely on gradient information. So that's this class of algorithms called quasi-Newton methods, and we'll look at a little bit at one of them to see how it works, and to understand the basic principle of how it works. Right, it's a huge topic. We don't have time to analyze it in massive detail, but at least you should get a little bit of a feel for how these quasi-Newton methods work and why they work reasonably well. Okay, so the obvious thing to do if you have gradients but not Hessians is actually just to slog out the Hessian using finite differences, and you absolutely can do that, and that can work pretty well. It's very computationally costly, and all of the kind of tricky issues of working out derivatives numerically using finite differences that we're going to study later on can really come to bite you. So there are problems where that is a possibility and you can do that, but it tends to come at a very big computational cost. So you get a more efficient method in terms of numeric number of iterations, but each iteration becomes very costly and potentially fraught with numerical issues. And so that turns out not to be a very attractive method in general, but is certainly a possibility for some problems. So the approach we're going to concentrate on is this idea of a quasi-Newton method. And essentially what you want to do is to try and build up an idea of the Hessian using recent function and gradient evaluations. Obviously at a particular point you can evaluate the function, you can evaluate its gradient, but if you know the function evaluations and the gradients for a collection of functions, then for a collection of points, then you can sort of get an idea what the gradient is without actually resorting to full-on, finite differencing to work out exactly what the Hessian is. You can build up a bit of an idea of what the curvature of the surface is in the vicinity of the point that you are at by using the function evaluations and the gradient evaluations from recent points. That's basically the idea. And there are a few tweaks on this. So one is that we've already discussed that when you're doing Newton's method, you're not guaranteed to get a positive definite Hessian at each stage. So we can sort of fix that within the context of this quasi-Newton method to make sure we're always dealing with a positive definite Hessian. But the other thing is that we'll look at is that rather than approximating the Hessian and then solving a linear system to find the Newton step, we can actually directly work with an approximation of the inverse Hessian, and then we don't have to solve a linear system at each step. It's just a simple matrix vector multiplication at each step, and that then saves a whole lot of hassle as well. So actually we'll start by thinking about approximating the Hessian, but then we'll switch to seeing what that means for approximating the inverse Hessian, and that's another big advantage of these quasi-Newton methods. So there are lots of cute things about these methods that, we're not going to study in massive detail, but we're just going to get an idea of what they are and why they work. So they date back to the 50s, but in fact, publications on it are more recent than that. But the particular variant we're going to study is this BFGS, named after 4 people. Around about the 70s, the cute comment at the bottom there suggests that you should remember this as big friendly giant steps, and it certainly is handy for remembering the acronym, I personally find. So there we are, BFGS is what we're going to look at. Okay, so let's just suppose that we're in the middle of applying this method. We're at step K. We know what theta k is. We know what our approximate Hessian hk is. And so just with any other Newton method, we now solve the linear system for the Newton step, and we get our new search direction, and we'll then get our new theta k plus 1, and that will either be directly the solution of that linear system, or we might do some kind of search before we accept it. But now we've got our new theta, we're going to call theta k plus 1, and the question is, how do we update our approximate Hessian h to get a new approximate Hessian h of k plus 1? Because to go on to the next step of the algorithm, we need our new estimate of the Hessian matrix. So what is the Hessian? Well, the Hessian is the thing that allows us to get a good quadratic approximation of our function. That's really fundamentally what it's all about. And so if we've got this new Hessian, then that's giving us a quadratic approximation to the function at step k plus 1, i.e. it's going to give us a quadratic approximation of the function about the point theta k plus 1. So if we just write down Taylor's theorem to second order, we get the usual Taylor series expansion, where we've got the function evaluation at k plus 1, we've got the gradient at k plus 1 in a linear term, and we've got a quadratic term involving this new Hessian. So what properties would we like of this Hessian matrix? Well, we would like it to give us sensible gradients for a start, but looking at the gradient at the point theta k plus 1 doesn't really tell us anything very interesting, because we know it gets the gradient exactly right at theta k plus 1 by construction, whatever the Hessian matrix is. So that doesn't really constrain what we do, so that's not a helpful thing to think about. However, what we can think about is what the gradient is like at our previous point, because we know the gradient at our previous point. That's something we've already computed, so we don't need to compute anything else to think about that. So we can make sure that our quadratic approximation at least has that particular gradient right. So that's a very weak constraint of all the things that we could possibly require, right? This is just one thing. We want the gradient to be exactly right at our previous point theta k. But that's a constraint that we can apply to our problem in order to think about how to update our Hessian. So let's think about how to do that. What we do is we just take the gradient of that quadratic approximation above to get this expression for the gradient of f. So, I mean, hopefully people can see where this comes from. So this first term here just drops out when we take the gradient with respect to theta, because it's constant with respect to theta. Then we've got this linear term in theta, which gives the first term in our gradient here. And then we've got this quadratic in theta, which when we take the gradient of it with respect to theta gives us this now linear term in theta involving that Hessian matrix. If these kinds of operations aren't very familiar to you, that matrix cookbook that I've referred to previously has everything you need to do these sorts of matrix vector calculus operations. So that's our gradient. And so our requirement is going to be that this estimated gradient here is exactly right at the point theta k. So let's now evaluate this approximate gradient at the point theta k. So that gives us the equation at the top of the page there. And if we just give the differences in the thetas and the differences in the gradients, the names, yk and sk respectively, then we get this equation 4 here, which is the so-called secant equation. I mean, the origin of the name isn't really important, but this equation here is known as the secant equation. And basically, if that equation is satisfied, then that's telling us that our estimate of the gradient at the previous point is exactly correct. So what we want to do is update our old estimate of the Hessian h of k to get h of k plus 1, and we want to do that in such a way that this secant equation here is satisfied. So there is a question about whether we can ever do that for a sensible positive definite h, and if you look at the degrees of freedom, usually you can, but there are some conditions on S and Y that you need in order to be able to do it, and we're glossing over those, but you can look them up if you need to know. It's easy to see, for example, that S transpose Y must be positive, right? So that's one of the conditions, and if that's not true, then you need to do your step selection slightly differently to make it true. But you can always do it. It's not a problem, but it just interferes with the step selection process. Right, but this secant equation is still massively underdetermined, right? There's loads of degrees of freedom in this Hessian matrix, and this constraint here is rather weak. So we need to constrain the problem a bit more. So what we're going to do is we're going to say, well, let's just consider a low rank update of our previous estimate of the Hessian. That seems like a smart thing to do. So probably the most obvious thing to do will be a rank 1 update of the Hessian, and you can do that, and there are methods that do that, but this BFGS algorithm uses a rank 2 update of the previous Hessian. So rank 2 update looks like the equation at the bottom of the page, right? That's a general rank 2 update, well, at least of a symmetric matrix. So that's our rank 2 update. We're going to take some weighting alpha of a vector u transpose and some other weighting beta of a vector v transpose, and we can choose the weights, and in principle we can also choose the vectors, but we don't have many vectors lying around, right? The obvious vectors lying around are s and y, so the obvious thing to do would be to plug in s and y, and we could do that, but it turns out to be a bit better to plug in y and h of s, okay? And if you look back at the secant equation, that y and h of s are sort of on the same scale, right? If we chose y and s, they're kind of different coordinate systems, and so it turns out to be more logical to use y and h of s in our choice, hk of s crucially, as our variables to do our rank 2 update of the Hessian matrix. So if we make those choices, we still have to choose alpha and beta to satisfy the secant equation, but it turns out if we substitute those choices of u and v into the secant equation, we can just then solve for alpha and beta just directly, just using simple matrix algebra. You can try it. You substitute in, you solve for alpha and beta, and you get this particular update of the Hessian matrix here. So our new Hessian matrix is the old Hessian matrix plus this rank 2 update, and you can see this is a rank 2 update involving y and h of s. Okay, so we do this rank 2 update. It satisfies the secant equation. We can actually just verify this by substituting this particular expression straight back into the secant equation, and you can see that it works. Okay, so this Hessian update works. So we could just do this, and this would all be fine. But what we said was that although we could do that, we'd still have to solve a linear system at each step in order to get the Newton step. So if we could think about a way of doing this without working directly with the Hessian, but instead working with the inverse Hessian, then we would save ourselves the cost of solving a linear system at each iteration. And because we've chosen to do this Hessian update via a low rank update, you should in the back of your mind be thinking about Woodbury's formula and the fact that we know how to do low rank updates of inverse matrices based on low rank updates of their inverse, the original matrix. So that's what you should be thinking about in the back of your head. So we just start by inverting that Hessian matrix we started from. So we're going to call B the inverse Hessian. So we just rewrite that formula we had previously using B instead of H, and it looks like that. And then we do immediately see now that we are dealing with a low rank update of an inverse. So we could actually try and slug out Woodbury's formula directly for this. It turns out to be kind of tedious actually, and the algebra gets a bit messy. But if you can guess the solution, just like with deriving or checking Woodbury in the first place, if you can guess the answer, it's relatively easy to check that it works. So here, if you sort of think about what's going on, you can see that actually the update is going to be given by this equation in the middle of the page here. And you can check by direct multiplication. So if you don't believe that this works, you can just check it by direct multiplication that this does in fact work. Okay, so that is consistent with the Hessian update that we had on the previous slide. And if we want, we could modify the secant equation, so we invert the secant equation so that it's now in terms of the inverse Hessian, and we can also try shoving in this update for B to check that it does in fact satisfy the secant equation, and again it does. So for various different reasons, we can see that this update, this nice low rank update of the inverse Hessian matrix does work and does meet our constraints. Okay, so we're just gradually updating the inverse Hessian at each step of our algorithm using this low rank update, and this is having this property that the gradient at the previous iteration is correct, as well as obviously the gradient at the current iteration being correct. And so this is hopefully using information from our sequence of function and gradient evaluations to get a better, gradually better and better approximation of the Hessian as the algorithm runs. Okay, so the update is usually written like this, but there's a question of how you evaluate this thing in an efficient and stable way. We've talked about that problem in chapter 2. So if we just expand this and simplify, we get the equation at the bottom. So this is more like the expression you would use as a basis for implementation. So you're starting off with bk, and you're going to modify bk in an additive way. Okay, so that's a good thing. And there are a few other things you can think about here, that, for example, this bk yk crops up here, but actually its transpose also crops up here and here. So the first thing you want to do is calculate bk yk and store that, and then you reuse that. And again, you want to think about what's the best order to evaluate these terms and update bk. But it's a relatively simple operation. You can do this in a reasonably efficient and stable way, and this then forms the basis of a very nice algorithm that is typically much cheaper than the Newton method. It doesn't require evaluating Hessians, which can often be problematic for reasons other than just computational, and it performs much better than steepest descent typically, and has performance reasonably close to that of a Newton method. Okay, so these algorithms are quite impressive. So just to make it absolutely clear, we now don't need to solve a linear equation to find the Newton step. We just directly multiply the negative gradient by this estimated inverse Hessian, and because of the way we've constructed the inverse Hessian, we know it's positive definite, so we know this is all going to work and it's not going to blow up or anything, and so that's our algorithm. the final question is, how do we start off the algorithm? We need a reasonable guess at the Hessian to get going, because remember, we're just doing a low rank update at each stage, so we probably want to start off with a reasonable estimate of the Hessian, and ideally also a positive definite estimate of the Hessian. So you usually start it off with doing something like finite differencing to get an initial estimate of the Hessian. So that's a computationally intensive operation typically, but at least you're only doing it once, and that will just get you started. And the same issues about if that is not positive definite, you maybe want to nudge it so that it is in some way. So yeah, you want to start off with a positive definite finite difference, maybe approximation to the Hessian, and then run your quasi-Newton method, which will then gradually update the Hessian estimate at each iteration. Yeah, and so we can look at how this progresses on the same function we've looked at previously. If I just rotate. So this is, again, we just clipped off the left-hand plots here, but just reading along left to right and then top to bottom, we see the progress of the algorithm, and it's making intelligent jumps in much the same way as the Newton method does. And in particular, it's progressing much faster than steepest descent. It's zigzagging a little bit more. If you look carefully and zoom in, it's zigzagging a little bit more than the Newton method does, but significantly less than steepest descent does. So it's this pretty reasonable compromise between steepest descent and a full Newton method. It is like almost the computational cost of steepest descent and almost the performance of Newton method, right? It's somewhere in between, but it's kind of getting the best of both worlds to a reasonable approximation. Yeah, so maybe it takes twice as many steps as the Newton method, but it's an awful lot cheaper, and so it's a pretty good compromise. And yeah, it's much better than steepest descent on many problems. So definitely something worth knowing about. So we've talked about the simplest variant of this quasi-Newton algorithm known as BFGS. There are various different versions of it, particularly for high dimensional problems, right? So in a high dimensional problem, you maybe wouldn't even want to store a Hessian matrix, right? If it's very high dimensional, your Hessian matrix is n by n, where your problem is n dimensional. Maybe even storing and updating the Hessian is a hassle, and you don't even want to do that. So there's a variant known as LBFGS, which doesn't actually store the full Hessian. It just keeps the recent function and gradient evaluations in memory and uses those to sort of implicitly store and propagate the inverse Hessian at each step using this low rank approximation. So it's just a tweak on the basic BFGS idea, but again is very popular. You'll see it referred to often in the literature. And if you want to know more about that and some of these other issues that we've skipped over, I've got a few Wikipedia links here for you to find out a bit more. So one last thing that I wanted to cover on kind of basic optimization theory is this Nelder-Mead polytope method, which basically is a method you would use when even gradients are a problem, right? So there are some problems where even calculating gradients is tricky. If you've got especially like a black box function, defined by a piece of computer code, just differentiating that can be an issue. You could use automatic differentiation that we'll talk about later, or you could use finite differencing. But sometimes, just even getting at gradients is problematic, and some functions are just actually not differentiable, and so that's then even more problematic. So it's good to have some methods in your toolbox for optimization that don't require gradients at all. So the Nelder-Mead method is one of the simplest. and one of the sort of least computationally intensive. So a lot of gradient-free methods for optimization would fall into the general class of methods called, computationally intensive statistical methods. But that's a different course as far as APTS is concerned. So we're just going to look at this Nelder-Mead method just to give you a clue about how you might go about optimizing a function in a reasonably intelligent way without any explicit gradients. And the intuition behind it is a little bit like the intuition behind quasi-Newton methods. So quasi-Newton methods were happy with gradient evaluations but didn't want to do full-on Hessian evaluations, but they kind of built up a little bit of a feeling for the curvature of the surface by using recent function and gradient evaluations to build up a picture, an informal picture of what the curvature might be like. And it's the same kind of idea with this Nelder-Mead method, that you're not explicitly evaluating gradients, but you are going to use recent evaluations of the function in order to get a bit of a picture of how the surface of the function is varying, to give you a little bit of a clue what the gradient might be like, which is then a little bit of an idea you can use to define a search direction, right? So that's the intuition. So we're going to use recent function evaluations in order to get an idea of which way is uphill and which way is downhill. So if you think about it, and in fact it's quite helpful, I think, to think about the 2D case first. So suppose theta is two-dimensional, so you're moving theta around in a plane, say, and you're evaluating your scalar valued function for different values in that plane. In order to get a direction in theta space, you really need at least 3 points, right? So if you've only got 2 points, you can only really define one direction. You need 3 points essentially to define a basis, yeah? So even to kind of figure out which direction is which, you need at least 3 points in two-dimensional space to be able to define a basis, to think sensibly about the different directions you could possibly go in. So it seems like you're going to need at least 3 function evaluations to be able to say anything sensible in two-dimensional space. And again, if you jack up to 3 dimensions, you've got a tetrahedron of points that you could then use to form a 3-dimensional basis based on, one of the vertices of your tetrahedron, and so on. So essentially, in n-dimensional space, you're going to want to have at least n+1 points in order to be able to just sensibly think about the different directions you could even go in that space. So that's going to be our starting point. We're going to imagine that we're going to maintain a set of n+1 vectors in our n-dimensional space, and there we'll define a polytope in that n-dimensional space. Okay, so in 2D, that polytope is a triangle. In 3D, that polytope is a tetrahedron, etc. And we're going to kind of carry through a set of n+1 points throughout our algorithm, and we're going to keep iterating the algorithm until we either find, hopefully, a minimum, or something goes horribly wrong. Okay, so if you do have a set of n-points and a set of function n+1 points and a set of function evaluations at those n+1 points, how might you figure out which direction to search in next, right? At least if you've got n+1 points, you can talk about different directions you might go in, so that's a good start. There are actually quite a lot of things you could do, and in fact there are lots of variations on these kinds of algorithms because of that. But the way the Nelder-Mead method works is really pretty simple. It says, well, start from the worst point. So if we're thinking about going downhill, that would be the point with the highest function evaluation. So we start at the first point, and at the worst point, and we know that is in some sense not the right direction, right? So we want to be heading in a different direction to that worst point. We want to be heading away from the worst point. And so what we do is we head away from the worst point, sort of through the center of the polytope, or at least through the center of the average, through the average of the remaining endpoints. So clearly, or at least if the function is reasonably well behaved, you know that all of the other points in your polytope have a better function value, and so hopefully when you evaluate the function at the average of them, then that's going to be better. But in particular, maybe if you just keep going, then things are going to get better still, right? You're heading sort of from a bad point through a set of better points, and so hopefully if you just keep going a bit, you'll head to somewhere even better. That's the intuition, right? So it's a very, very simple idea. You just go from the worst point through the average of the rest and keep going, and hopefully that's taking you downhill if you're doing a minimization. So yeah, so your initial step length is typically set to twice the distance from the worst point to the centroid of the others. So you kind of go through the centroid and on. If that works, okay, so that new point is certainly better than your worst point, then maybe you could try going a bit further and just take the better of the two. So that's going to be a new point. And it might not be the best point, right? But as long as it's better than your worst point, then you're happy that you've now got a set of, you could discard that worst point and you'll now have a set of points that's better. If that doesn't work, right, so if neither of those actually work, then you can try just shrinking a little bit as well. And if that still doesn't work, then what you can do is find your best point and then shrink your whole polytope linearly towards that best point, maybe like shrinking in a factor of 2, say. You can choose your factor. So you shrink your entire polytope towards that best point, then hopefully you've now got a set of better points and you can try the whole thing again and see if the whole thing now works. Yeah. So there are sort of multiple levels of sort of bailouts if things don't work, right? So you try it first. If that doesn't work, then you try shrinking your points, your step lengths, and if that doesn't work, you try shrinking the whole polytope towards your best point. So this is all very ad hoc, but it's all quite simple. These are all very cheap operations, and so you can actually shrinking the polytope isn't, because you've now got to reevaluate your function at each one of those points. So that one's a little bit more expensive, but they're cheap operations. There's no derivatives involved, and the idea is you're just kind of wandering in a semi-intelligent way downhill along your function. Yeah, and obviously if you accept a point, then you get rid of the old one, your old worst one, so you've now got a new set of n+1 points, but on average they're clearly better. Okay, and there are all kinds of basic tweaks on this algorithm. Yeah, there are all sorts of things you could do to vary the factors that are used in this algorithm, but this basic crude method works surprisingly well in practice, as we'll see. So here it is on this Rosenbrock function. So obviously this is just a 2D input space. So your polytope is a triangle of 3 points. So you've got to initialize it with 3 points, and so you've got to think about a sensible way of initializing it. But here it's just been initialized up here with 3 points, and then we're going to see what happens when we iterate the method. So that's the worst point, and then so you head off in this direction, so then you get rid of that worst point, and now that's going to be your worst point, so you're going to head off in this direction, then you're going to get this point, etc. And so your polytope sort of walks around the function and gradually wiggles its way towards the optimum. Okay, so that looks to have worked on that function, and it has worked on that function. It took 80 steps there to get to the minimum. That's a bit more than the BFGS algorithm we've just looked at, but it didn't require gradients. And so actually, in terms of pure computation, this is the cheapest method we've looked at so far, and it worked perfectly well. Yeah, so it's derivative free. All we have to be able to do is evaluate the function. It just walks its way to the optimum in a semi-intelligent way. It takes a bit longer than BFGS, but at a very low cost. So, it looks kind of cool. But in fact, this Rosenbrock function is not a difficult function, and this is a relatively low dimensional problem, etc. So it certainly doesn't always work this well, but again, it's just a good algorithm to have in your toolkit. If you really need to semi-intelligently optimize a function where you really can't evaluate derivatives, then this is something you could try. There are lots of little wrinkles. There are lots of ways it can go wrong, but broadly speaking, if you can afford to maybe run it a few times from different starting points, you can maybe restart it from an optimum to make sure it hasn't just got stuck somewhere, from an apparent optimum to make sure it hasn't just got stuck somewhere, etc. Then it can give you a reasonable answer reasonably cheaply. Yeah, so if you don't need to know things too accurately and you can fiddle with it a little bit to get it to work, then it can be pretty good. But it tends not to be used as an algorithm underpinning general purpose software because it can go wrong in various ways. So it's not super robust like a Newton method either goes horribly wrong or it works, whereas there's a little bit more to it than that. So that's more or less it in terms of the general kind of optimization methods I wanted to talk about. But obviously, it's a huge topic, right? You'd have entire lecture courses on optimization. So what else is it worth just mentioning in passing? So obviously, we're thinking primarily about statistical applications. Very often, we are interested in maximizing likelihoods, or even log likelihoods. In that context, the method of scoring is often used, but in many cases, that's exactly the same as Newton's method, and in other cases, it's very similar to Newton's method because it just replaces the Hessian with the expected Hessian, which in some contexts is a more natural thing to think about. So that's just a trivial tweak on Newton's method. It's more or less the same. Gauss-Newton is again very like Newton's method, but effectively using an approximation to the Hessian. So again, is a little bit reminiscent of the quasi-Newton methods as well, but it's an approximation that makes sense when you're working with a simple least squares problem. Yeah. So if your optimum is a least squares, your objective function is a least squares function, then Gauss-Newton can be applicative. But again, it's sort of like Newton, sort of like quasi-Newton. It's just a slight variation. And in fact, both of these methods here are relevant in the context of fitting generalized linear models. Okay, so obviously generalized linear models crop up a lot, and people have spent a lot of time thinking about the best ways to fit those. Actually, a straight Newton method generally works pretty well with GLMs, but these two variants are often used in that context as well. So we said that steepest descent is a little bit clunky for various reasons, because this idea of heading in the steepest possible direction downhill, although intuitively it's very appealing, actually it's not very smart. And so we've seen that Newton's method does a much better job by using the fact that it knows a bit more than the gradient, and so it can use the curvature in order to make a much smarter choice of direction. In fact, there are other things you can do to make your direction choices a little bit smarter, and conjugate gradient methods are a kind of class of methods which attempt to do that. So one of the issues with steepest descent is if you do a real line search to really optimize at each step, then it's clear that your next search direction is by definition going to be orthogonal to that, right? Because you've already optimized in that direction. So you're always kind of heading off at right angles for each different search step, and that isn't always a very good idea. So conjugate gradients does something a bit smarter by choosing a set of directions that would be guaranteed to get you to the bottom of a quadratic in n steps. Yeah, and obviously your function that you are optimizing is typically not going to be a quadratic, but it turns out that actually that algorithm gets you downhill typically quite a bit more efficiently than straight steepest descent. So that's something worth knowing about as well. I've already hinted at simulated annealing, so this is one of these computationally intensive methods. So this is again to be used when gradients are problematic, but it uses stochastic methods to sort of randomly explore your function and drift downhill using noise to kind of stumble upon good directions as opposed to heuristically trying to find them. This can work very well when your function is cheap to evaluate, not so well when your function is expensive to evaluate. But again, I would say this really falls into the class of computationally intensive statistical methods. It's very closely related to things like Metropolis-Hastings algorithms for exploring probability distributions, etc. So it really makes sense to study that more in the context of one of those courses. Something else that's become quite popular in the last few years is stochastic gradient descent. So the idea of this is that if you are calculating a gradient, very often in statistical contexts, your gradient will be calculated as the sum over a large number of data points. Yeah, so you'll be, when you code it up, you'll be summing over lots of terms, and each one of those terms will correspond to a data point in your data set. So the initial intuition behind stochastic gradient descent is, can we just make a crude approximation of what the final gradient will be on the basis of a random sample of data points, yeah, and then we scale up, right? Lots of statistics works like that. We take samples and we scale up to get a population estimate. Can we do the same with gradients? Can we just look at the gradient on the basis of a random sample of observations and then scale that up to an estimate of gradient on the basis of all observations? And you can, and that does often work very well, but there's a sort of surprising additional bonus advantage as well. So obviously the motivation there was that will be computationally cheaper, because instead of summing over a huge number of points, you're now summing over a much smaller number of points, so your gradient evaluation is cheaper. But in fact, the random aspect of choosing a random sample and forming your estimate of gradient on the basis of a random sample injects some noise into that gradient estimate, and that noise can be helpful, right? So it can be a bit like the simulated annealing method from the previous slide, that actually having a little bit of noise and allowing yourself to stumble in good directions rather than always just heading in the steepest direction downhill can actually be helpful. And so just throwing a little bit of noise into your gradient estimate can actually sometimes be a good thing. So perhaps slightly surprisingly, by using this poorer estimate of the gradient, but essentially a slightly noisy estimate of the gradient, can be helpful, can speed up convergence. And so there's been lots of interest in these algorithms in recent years, and in particular they're used a lot in the context of optimizing neural networks. So that's where lots of people use these today, but they can be used in many optimization contexts. Whenever your gradient is a sum over a large number of terms, you can think about using these stochastic gradient methods, and they're not going to compete with a Newton method or anything like that, but they're cheaper than gradient descent and can work better than gradient descent. So if you're in a situation where you would be otherwise using steepest descent, then they can have advantages. Again, something that's a little bit orthogonal is the EM algorithm, but you'll see that referred to a lot in the statistics literature. So this is the expectation maximization algorithm, and it's when your likelihood, the likelihood that you want to maximize requires marginalization over a set of nuisance variables, often, for example, random effects. And so in that context, you kind of alternate between an expectation step where you're sort of integrating out the missing data or nuisance variables, and a maximization step where you maximize the likelihood. Again, it's a little bit orthogonal to what we're talking about. It's very much specific to a certain class of likelihood problems, but again, it's something you'll see reference to in the literature. The only other thing I want to discuss before we leave the topic of optimization completely The problem of constraints on your optimization. So far we've been thinking about having a completely unconstrained parameter space theta. We've essentially been assuming that it's Euclidean space. We haven't said it explicitly, but that's essentially what we've had in the back of our minds. We certainly haven't been imagining problems associated with wandering off the edge of our space, which is can be a real problem in practice. So, a good example of that would be you'd have a parameter set theta, but one of your components, theta 1, say, actually has to be non-negative, right? So maybe it represents a variance, for example, and it just can't be negative. So what could you do in that case? Well, the simplest thing to do is just to reparameterize so that you don't have constraints. So in the case of a non-negative random quantity, you could just define a new random variable, which is a log or exponential transform of the original, and you just work then on the constraint space. Yeah. So if you flip back and forth with exp and log, you're going to fix the problem, and so you've now taken this constrained space and mapped it onto an unconstrained space, and you're now free to wander in that unconstrained space because you know that when you map back, say via the exponential function, to your original parameterization, you're guaranteed to get a positive number. Yeah, so that's very simple and can work very well, but it doesn't actually solve all problems. So it's not like it's a magic solution to all constrained optimization, because it definitely isn't. So what could go wrong? Well, there are often constraints that can't be expressed in this simple way. So that would be the first problem that you might have, that it might not be as simple as your parameter has to be bigger than 0. It might be some more complicated constraint than that. It can also be the case that when you do this reparameterization, you're changing the surface, right? You're changing the surface that you're trying to optimize, and it could be that the original surface you had was better behaved than the reparameterized surface, and so you actually make the optimization problem more difficult by reparameterizing it to get rid of constraints. Okay? And so that can be an issue. There's also an issue that if, for example, you're dealing with a parameter that has to be non-negative, for example, and in fact maybe it even has to be strictly bigger than 0, but actually if your optimum is very close to that value, possibly even that value, right? So you can get a situation where you've got a variance term, for example. You know that has to be non-negative, but actually your likelihood is like bunched up right against 0, and in fact your maximum likelihood estimate really would be 0. Yeah, that does happen in various problems. In that particular case, you've got a bit of a problem if you reparameterize with log, because then your reparameterized parameter just runs off to minus infinity because it's trying to get as small as possible, but the only way it can do that in the unconstrained space is to run off to minus infinity, and that causes problems as well, and your function is going to get them very flat as you head off towards minus infinity, and it's just not as simple always as introducing a simple reparameterization and hoping that everything will be fine. Sometimes it isn't fine. So what else could you do? Well, one thing you do is then add a penalty, right? So, for example, if a function has to be, if a parameter has to be non-negative, then you just add a penalty to your objective function that really penalizes negative values. Yeah, so that would be another thing you can do, and that can work extremely well. But again, it's quite delicate because you've got to really carefully choose the penalty. You don't want to make the objective function more awkward, and in fact, you nearly always end up making the objective function more awkward because, for example, the non-negative case, you'd like to add a big step at 0. So that as soon as you jump beyond 0 to negative values, your objective function jumps up. But then that puts a big discontinuity in your objective function, so that turns out not to be a good idea. So you want to have a smooth penalty that you're adding, but you want it to be sharp enough that you are effectively discouraging negative values, etc. Okay, so these are the kinds of issues. So this can work well, but you do need to be very careful with exactly how you penalize constraint violations. Ideally, you wouldn't do that. So ideally, what you do is you directly manage the constraints. And this is easiest to understand in the context of linear constraints. You can actually, if you've got linear constraints, right, so say a linear combination of variables has to sum to 0 or has to sum to some other number, you can actually directly embed those constraints into your optimization procedure, right? So for example, if you've got a Newton method and you're calculating a Newton step either by solving a linear system or by just applying a matrix multiplication, if it's a quasi-Newton method, you can directly build those constraints into those steps to ensure that each step that you execute doesn't violate those constraints. Yeah, so you can actually put the constraints into your optimization procedure. And if you can do that, then that's nearly always the best thing to do, but not all problems can do that. So for linear constraints, these optimization methods that are based on basic matrix computations, they can very often be adapted quite easily to handle linear constraints, but non-linear constraints can be more problematic. Let's just leave it at that. Yeah, and sometimes, I mean, we've talked about reparameterization. We also, I guess, briefly mentioned the idea of adding a penalty into the objective function. There are other ways you can modify the objective function as well. Simple reparameterization, not to apply constraints, but just to change the parameterization of the problem can change the surface, and sometimes in a good way. So a classic example would be very often it's better to work with precisions than variances, right? So you can most naturally often write your likelihood function in terms of variance, but actually its reciprocal precision often makes more sense. And you may have discovered this in terms of mathematically dealing with likelihoods, that it can often be more convenient to work with precisions than variances. And similarly, computationally, the surfaces can sometimes be better behaved in terms of precisions than variances as well. So that's something to know about, that sometimes just a reparameterization can just make your surface slightly better behaved. But that's parameterizing the problem, right? So that's changing the input parameters. You can also just change the objective as well. Now, you might want to use a monotonic function if you're going to transform the objective function, right? You don't want to change the locations of your minima necessarily. But something like the log function would be a nice example of a monotonic function. So if you've got a strictly positive function, then you at least have the option of applying log to it. Okay, so if it's not strictly positive, then you can't do that. But if it's strictly positive, you could log it. That will typically be a nicer function in many ways, and in particular, it will typically be more convex, and that is often good for the properties of these optimization algorithms. So that's something to be aware of as well, that sometimes just transforming the objective can make your function a bit nicer. And again, in the context of statistics, we're often dealing with likelihood functions, and we know for all kinds of reasons that log likelihood functions are typically much, much nicer than likelihood functions numerically, but also just from a mathematical function surface point of view, the log likelihood is just a nicer object to work with. Yeah, basically in all ways. So you nearly always want to work with a log likelihood rather than a likelihood. Another thing you can do is just perturb the problem slightly. So you might be just unlucky, right? You've got an optimization problem. That objective function, it's a function of your data. It could just be that your data are just, make the surface just a little bit funny, and sometimes just perturbing the data, or as we've hinted at already, just redefining the objective function based on a subsample of your data can be a way of at least getting started with a problem, finding roughly where the optimum is, and then you can always, go back to your full data set once you know roughly where your optimum is, etc. Resampling your data slightly, resampling the subset you're working with can help to, again, allow you to jump out of a local minima to get, to some better minima as you go along. And of course, a lot of this is very reminiscent of the stochastic gradient descent idea that I've already talked about. Yeah, and sometimes you just need to reevaluate your problem completely. So that logistic map problem that we looked at previously to see what can go wrong when you just try and maximize an objective function. So in that case, it was the chaotic dynamics of that logistic map was really making your optimization function horrible. But maybe least squares, fitting isn't the best thing to do with a chaotic dynamical system. And well, people generally agree that it isn't the best thing to do with a chaotic dynamical system. But what you could do is match some properties of the data. So instead of exactly trying to match each observation, you could say, well, it's pretty hopeless to try and figure out how to match each observation because this system is very unpredictable. Instead, I want to get the behavior right. So I'd like to get the correlations between observations correct. So I might want to get the variance of the observations right. So if you start matching the means, the variances, the lag 1 correlation, the lag 2 correlation, ultimately perhaps the whole autocorrelation function, maybe matching those would be a better thing to do. So maybe if I redefine my objective function in terms of some statistics of the data set rather than worrying about matching individual observations in some least squares penalty, maybe that would be a better thing to do. And if you try that with that problem that we talked about, it turns out that you get much better behaved objective functions, and your fitting is much more reliable, even in the kind of chaotic regimes, if you adopt that kind of approach. Okay, so you're going to want software if you're using R. Your kind of go-to functions are probably going to be Optim and NLM, so make sure you know how to use both of those. But there are lots of packages as well, depending on your problem, right? So, we've sort of discussed optimization. It's a very big area. There are lots of custom methods that are specifically designed for specific kinds of problems and specific kinds of constraints, and whether you can get gradients, whether you can get Hessians, etc., the nature of the constraints that you're applying. And so you need a different algorithm, a different toolkit, depending on the exact nature of the problem that you're interested in. So there are lots of add-ons that you can get from CRAN, but your starting point is nearly always Optim or NLM. So do have a look at those. There's also the interesting question about whether you should just implement your own, and we're going to look at that in the practicals, etc. Should you write your own Newton method? Should you write your own quasi-Newton method, or should you just use a library version? Well, in the context of matrix computations, I was pretty clear that you absolutely shouldn't ever write your own matrix code, right? You shouldn't ever write your own code to multiply two matrices together or do a matrix vector multiplication, etc. You should always use the library code because they'll just be, much better, much more robust, much faster, etc. So it's pretty clear in the context of matrix computations, and especially for low-level operations, you should just use the library code, and you shouldn't really ever even think of writing your own, other than to understand how they work, of course, and that's always the case. But for real problems, you should use library code. For optimization, it's not quite so clear. So you probably do want to use library code in the majority of cases. The advantage of using your own implementations is that they can be tweaked and you can understand where they're going wrong much better. So if your optimization library code works, that's great. But if it doesn't, actually digging into why it didn't work and getting diagnostic information out of the library code can be tricky. Whereas if you're using your own code, you can customize it, you can tweak it, you can add in your own diagnostic output, you can add in your own little fudges that are specific to the particular problem that you're trying to optimize, etc. So you obviously have a lot more flexibility with your own code. So sometimes people do write their own optimization codes, and sometimes there are good reasons for it. But by and large, you should be using the library implementations. And in terms of further reading, well, again, it's a huge area. There are lots of very good sources on optimization. But in fact, this first book on the list here, Know, Still and Write, Numerical Optimization, is a good text covering a lot of basic issues that arise in the context of optimization. So that's a good place to start for learning a bit more about optimization, and then you can go off into specialist literature if you need to go further than that. So that's it for optimization.